and welcome to Virtual Class 10. Today is Tuesday, May 5th. Right now, many of you are taking your exam, and I just wanted to take a few minutes to say thank you for all of the hard work that you've been putting in, all of the assignments that have been coming in. I've been very proud with how well you've been doing. Today, I'm making a special video. There's no new content. Instead, I'm going to give you a few pointers and tips about completing the lab report that I've posted today. Please make sure that you try and watch this entire video because it's going to go over how to answer some of the questions that are included on the lab report. As always, when you're done with your lab report, please scan it as a PDF and submit it using the Dropbox. So I'm going to turn it over to Kevin Orlando, who's going to go through how to complete the pre-lab questions and make that portion of the lab a little bit easier. Thanks very much. Thanks, Kevin. I wanted to take a minute and go over the pre-lab questions with you for this lab because they're kind of challenging. You may not immediately understand what they're all asking for, so I wanted to make sure to go over this with you. They also resemble the questions that you're going to find at the end of the lab. So if you continue reading on in the lab, you'll see that I actually gave you a data table that has all of the data that you would collect had you done the lab. What I'm asking for you to do is to simply finish out the calculations and answer the questions, the conclusion questions, before you submit it. So the first thing that I want to explain to you is what's going on here in this lab. Now, hopefully you've watched the video on molar volume of a gas lab that I included in the folder. That actually does a really good job at a slow pace of going through exactly what you're doing to set up the lab, and it explains how the hydrogen gas is collected. So what I wanted to do is to show you just a quick recap of that. So when you flip over your tube and the hydrochloric acid, which was at this end of the tube, goes down to the bottom, it starts reacting with the magnesium down here and generates hydrogen gas bubbles. So you might see bubbles going up the tube if we were doing this in class. And eventually there would be enough bubbles that the entire water level at the top of the tube begins to go down. The reason why it was important to use a one-hole stopper is because as the hydrogen gas is being generated, it's displacing the water that was in the tube. That water needs to go somewhere. So having a one-hole stopper allows the water to exit through the bottom of the eudiometer as the hydrogen gas is collected. The other part that I didn't think the video made clear enough was the fact that when you collect a gas over water, you actually have a mixture of two different gases at the top of the tube here. So as you can see, the mixture includes both the hydrogen gas that you were aiming to collect and water vapor. In fact, anytime you collect a gas over water, mixed into that gas that you're collecting is some water vapor. So the first question on the pre-lab assignment is actually asking you to calculate how much the hydrogen pressure is without that water vapor. So you kind of have to subtract that out. So we're going to use Dalton's law in order to do this. So one of the things that you do at the end of this lab, had we done it in class, is you move the tube into a large cold beaker of water and you get the volumes to equal each other. The purpose of doing that is to calibrate or equilibrate the pressure in the room with the pressure inside of the eudiometer. So they don't give you a pressure of the gas inside the eudiometer. Instead, they give you barometric pressure, or the pressure of the room. I'm going to call it P sub lab, so it's the pressure inside of the lab. So when you lower that eudiometer into the tube, the pressure inside the atmosphere, the lab around, is equal to the pressure inside the tube. Now, the pressure inside the tube, as I mentioned, is made up of two components. So it's made up of hydrogen and it's made up of water vapor. So if you're looking for just the pressure of the hydrogen, then you have to take the pressure of the lab and subtract out the pressure of the water. So in our case, they give us the pressure in the lab as 746 mmHg. And they tell you it is at a temperature of 22 degrees Celsius. Now, that's important because the vapor pressure due to water changes. So at 22 degrees Celsius, water has a certain vapor pressure. At a different temperature, the vapor pressure of water is different. It's not a constant. there's a small table in your lab that actually has 5 or 6 different temperatures and the water vapor pressure that matches up with that temperature. In this problem, the problem is at 22 degrees Celsius. So the vapor pressure due to water at 22 degrees Celsius is 19.8 mmHg. So we're going to subtract those two, and that will give us the vapor pressure just due to the hydrogen. And that turns out to be 726 mmHg. So that is your answer to question number 1. Now, question number 2 says, use the combined gas law to calculate the corrected volume at STP. So watch your units for temperature and pressure. So as a reminder, STP means standard temperature and standard pressure. Standard temperature is 0 degrees Celsius or 273.15 Kelvin. Standard pressure is equal to 1.00 atm, or in this case, since we're using mmHg, it's equal to 760 mmHg. So for problem number 2, since it's a combined gas law problem, I'm going to start by writing out all of my variables on the side here. So I'm going to have P1, V1, T1, P2, V2, and T2. So the pressure of the hydrogen initially when we collect it in the lab is 726 mmHg. The volume of that hydrogen, it tells you earlier in the problem, above problem number 1, there's a small paragraph that says the volume of hydrogen gas collected was 31.0 milliliters. And the temperature, as I mentioned earlier, was 22 degrees Celsius, which is 295 Kelvin. I'm going to stick with 3 significant figures throughout this problem. So the new pressure, the pressure at STP, so I'm going to just remind us all here, STP is 760 mmHg. We are calculating the new volume, and temperature 2 is 0 degrees Celsius or 273 Kelvin. So I'm going to use my combined gas law, P1 V1 over T1 equals P2 V2 over T2. I'm going to solve for V2. So V2 is going to equal P1 V1 times T2. So this T2 comes up here, solving for V2. And on the bottom, I'm going to have this P2 comes down here. So I'm going to have T1 times P2. Hopefully everyone's following along. Okay, so the next thing that we need to do is we need to solve for this volume. And remember, this is the volume that is corrected for STP conditions. So I'm going to plug in all of my values. So I'm going to start off 726 mmHg. My volume 1, which is 31 milliliters. My temperature 2, which is 273 Kelvin, I'm going to divide that by my temperature 1, which is 295 Kelvin, and my pressure 2, which is 760 mmHg. So I wind up for volume 2 with a calculated volume of 27.4 milliliters. Now, some of you might be asking, don't we measure pressure in ATM? Don't we measure volume, for that matter, in liters? And the answer to both of those is yes. But that only really becomes important when you try and plug it into PV equals nRT. Right now, when we're working with Dalton's law, so partial pressures adding together, if we're working with the combined gas law, the units don't matter as long as you're consistent. So I had to have both of these in mmHg. And since I solved for volume, my volume ended up coming out to be milliliters because I used milliliters in the problem. Noticing how mmHg crosses out and Kelvin crosses out. So far we have 2 numbers. We're going to hang on to this for just a minute. I'm going to wipe this board clean, and then we're going to move on and answer questions 3 and 4 of the pre-lab. Be right back. Okay, we are back. So I do want to read over question number 3. It says, what is the theoretical number of moles of hydrogen that can be produced from 0.028 grams of magnesium? I have that written down right up here. And it gives you a hint, refer to equation 1, which is what I wrote right here, for the reaction. So first thing I would like to do is to balance this equation. So if you notice, I have 1 magnesium here, 1 here, 2 chlorines. So I'm going to put a 2 here and 2 hydrogens, and now I have 2 hydrogens here. So these are all 1s. The second thing that I want to talk just briefly about are the states of matter. Now, you're not going to be tested on this, but I want to keep all of this in your mind because it's important to me that you see how all of this connects together. So first of all, magnesium. I wrote it down as a solid. The reason is it's solid, it's a metal compound. The only metal that's not a solid at room temperature is, hopefully you said mercury, good. The second compound up here is hydrochloric acid. Hydrochloric acid is one of our 7 strong acids. So in water solution, it actually dissociates into hydrogen ions and chloride ions. But for our purpose, just writing aqueous is sufficient. And of course, it is a halogen, which is also why it's aqueous. On this side, we have hydrogen gas. Think about it. In terms of bonding, hydrogen is nonpolar. So therefore, it only has LDF forces. LDF forces are weak, and they get stronger as the molecule gets bigger. But this is the smallest molecule imaginable. So of course, it's going to have very weak LDF, and it's going to exist as a gas. And then finally, MgCl2, ionic compound. When it's in water, it's aqueous, has a halide in it, which also tells us that it's aqueous when it's in water. So using these 2 pieces of information, let's go ahead and calculate our theoretical moles of hydrogen, which is what question number 3 is asking us for. So I'm going to write question 3 up here. We're going to start off with 0.028 grams of magnesium. Of course, the only place you can go from grams is moles. So we're going to have 1 mole of magnesium, and that is equal to 24.31 grams of magnesium, the mass off the periodic table. And then our mole ratio, so in this case, we have 1 mole of magnesium for every 1 mole hydrogen. So it's not going to change our answer numerically, but it will change it unit-wise. So when you multiply all of this out, it turns out to be 0.00115 moles of hydrogen. That's an incredibly small amount of hydrogen, but of course, we're looking at an incredibly small volume, so we're not going to get many moles in such a small volume. Now, this is our theoretical moles of hydrogen. And now we're ready to answer question number 4. So question number 4 says, divide the corrected volume of hydrogen by the theoretical moles of hydrogen to calculate the molar volume in liters per mole. Now, we have the corrected volume from earlier. So our corrected volume was 27.4 milliliters. Now, before I use this, before I divide it, just like the question asked, does anyone see a problem? Yeah, there's a problem. We're looking for an answer that is in liters per mole, and right now we have milliliters. So before I actually use this, I'm going to take this 27.4 milliliters and I'm going to convert it, so 1,000 milliliters in 1 liter, I'm going to convert it into liters. So we're going to get 0.0274 liters. Now I can take that volume and divide it by my theoretical moles. 0.00115 moles. And in this case, I'll get an answer of 23.8 liters per mole. So, of course, we remember, hopefully, from a few classes ago that the molar volume should be the accepted value or the literature value as it uses in this lab is actually 22.4 liters per mole. And we talked about that the other day. That's the value that you would get if you plugged in exactly 1 mole, so letter N in PV equals nRT would be 1 mole, and you plugged in STP conditions, so 1 atmosphere and 273.15 K. You would wind up with this volume per 1 mole. Alrighty, so I have given you the basic framework of what you're going to do in terms of the calculation. If you notice throughout the lab, I tried to put in little comments to make sure that you understood what you were supposed to be doing. In some of the questions, you'll notice I set up basically subtraction problems or multiplication, whatever the case might be, to have you fill it in, just to kind of give you that scaffolding to help you answer those questions. All right, that is all for me. I'm going to throw it back to Kevin at the desk. Hope everyone had a very nice Tuesday. I know everyone did really well on their test, and I will see you again soon with virtual class 11. Thanks very much. Thanks very much, Kevin. All right, that's it for today. Good luck completing the rest of the lab. Please let me know if you have any questions. On Thursday, we're going to start our last unit on thermochemistry, so look forward to virtual class 11 coming out very soon. Thanks a lot. Bye-bye, everyone.